In this video, we're going to focus on acid-base titrations. We're going to talk about titration curves and how to calculate the pH at various points of the acid-base titration process, and some other problems as well. So let's start with this one. 28.9 milliliters of H2SO4 was completely titrated with 38.4 milliliters of a 0.25 molar sodium hydroxide solution. What is the concentration of H2SO4? So how can we find the unknown concentration of this acid? So there's two ways in which we can do this. We could use stoichiometry to get the answer, or we could use an equation. Let's do it both ways for the sake of learning. So let's begin by writing a balanced chemical equation. Sulfuric acid, H2SO4, is going to react with sodium hydroxide. So this is an acid-base neutralization reaction. Sodium is going to pair up with sulfate. Sodium has a positive 1 charge. Sulfate has a negative 2 charge. So when you pair these two together, the formula is going to be Na2SO4. The hydrogen ions will react with the hydroxide ions to create H2O. So whenever you add a strong acid with a strong base, they will completely neutralize each other, creating salt and water. Now let's balance the equation. So we have 2 sodium ions on the right, which means we need to put a 2 in front of NaOH. Now notice that we have 2 hydrogen ions, 2 hydroxide ions. That's going to create 2 water molecules. So now the equation is balanced. So how can we use this equation to calculate the concentration of H2SO4? Well, let's start with the other substance, that is sodium hydroxide. Let's start with the volume of the NaOH solution. So we have 38.4 milliliters of sodium hydroxide. And let's convert that to liters. 1 liter is equal to 1,000 milliliters. Now the next thing we need to do is we need to use the molarity of the solution to convert liters to moles. A 0.25 molar solution means that we have 0.25 moles of solute, in this case the solute being sodium hydroxide, per 1 liter of solution. So now that we have moles of sodium hydroxide, we can convert that to the moles of H2SO4 using the balanced chemical equation. So the molar ratio is 1:2. For every 1 mole of H2SO4 that reacts, 2 moles of sodium hydroxide will be consumed. So right now we have moles of H2SO4. To get the concentration of H2SO4, we need to take the moles and divide it by the liters of solution. And we are looking for the original concentration of H2SO4. So we need to use the original volume of that solution. Let's convert 28.9 milliliters into liters. To do that, we need to divide it by 1,000. So 28.9 milliliters is 0.0289 liters. So now let's go ahead and plug this in. It's going to be 38.4 divided by 1,000 times 0.25 divided by 2 divided by 0.0289. So the concentration of H2SO4 in the original unknown solution, it's not an unknown solution, but the concentration was unknown. That unknown concentration, we now know what it is. It's 0.1661 H2SO4. Now let's talk about another way in which we can get that same answer. We could use this formula. M1V1 is equal to M2V2, but we're going to need to modify it a bit. So M1V1, let's relate that to H2SO4, and NaOH is going to correspond to M2V2. So in order for this equation to work, we need to take into account the 1:2 molar ratio of H2SO4 and sodium hydroxide. And the way we could do that is by looking at the number of protons in sulfuric acid and the number of hydroxide ions in the NaOH formula unit. So in one formula unit of H2SO4, there are 2 protons. And in one formula unit of sodium hydroxide, there's only 1 hydroxide ion. So once you incorporate that, this formula is going to work. So remember, M1V1, that's going to be the information for H2SO4. M2V2, it's going to correspond to the information for NaOH. If you mix it up, it won't work. So we're trying to calculate M1, the original concentration of H2SO4. V1, the volume of H2SO4, is 28.9 milliliters. M2, the concentration of sodium hydroxide, that's 0.25 m. V2 is 38.4 milliliters. Now, V1 and V2, they have to be in the same unit. If V1 is in liters, V2 has to be in liters. If V1 is in milliliters, V2 has to be in milliliters. So these units will cancel. Now, since M2 is in molarity, M1 will be in the same unit, molarity. So on the left we have 2 times 28.9, which is 57.8 times M1. On the right we have 0.25 times 38.4, which is 9.6. So now let's divide both sides by 57.8. So 9.6 divided by 57.8. That will give us the original concentration of H2SO4, which is 0.1661. So those are the 2 ways in which you can solve this particular problem. Number 2, 23.6 milliliters of a 0.46 molar monoprotic acid solution was titrated with a 0.19 molar sodium hydroxide solution. What is the volume of NaOH that should be added to the solution in order to reach the equivalence point? So we have a monoprotic acid. That's an acid that can give away 1 proton per formula unit. H2SO4, this is what is known as a diprotic acid. It can release 2 hydrogen ions per formula unit. So we're combining a monoprotic acid with sodium hydroxide. And we could use this formula. M1V1 is equal to M2V2. There's 1 proton per formula unit here and 1 hydroxide per formula unit there. At the equivalence point, the number of moles of H plus is going to equal the moles of sodium hydroxide. Therefore, we could use this formula to calculate the volume of NaOH that will be needed to take us to the equivalence point. Because at the equivalence point, these 2 must be equal. And if you take the molarity of HX and multiply it by the volume, it's going to give you the moles of HX. And that's going to equal the moles of H plus, since these 2 are in a 1:1 ratio. Likewise here, when you multiply M2V2, you have the moles of NaOH over the liters times the liters of the solution, and that will give you the moles of hydroxide. The bottom line is that we could use this formula to get the equivalence point. So let's go ahead and do that. The concentration of the monoprotic acid is 0.46, so that's M1. V1 is the volume of that monoprotic acid, so it's 23.6 milliliters. M2 is 0.19, and we're trying to calculate the volume of base that we need to add to reach the equivalence point. So we're looking for V2. So let's divide both sides by 0.19 m. So those units will cancel, and we're going to get V2 in milliliters. So it's 0.46 times 23.6 divided by 0.19. So the volume that's needed to reach the equivalence point is going to be 57.14 milliliters. And so that's it for number 2. Now let's focus on acid-base titration curves. And let's begin our discussion with a strong acid, strong base titration. So based on the order in which it's written, initially we have strong acid in the solution and we're adding strong base to it. So let's draw the titration curve for this type of situation. So initially we have strong acid in the solution. So the pH is going to start out very low. And then it's going to rise dramatically, and then it's going to eventually taper off. For a strong acid, strong base titration, the pH of the equivalence point is 7. And this is the volume at the equivalence point. Now, anytime you add base to a solution, the pH is going to increase. Now, the reverse is true if we have a strong base, strong acid titration. Anytime you add an acid, the pH will decrease. So this graph is basically just going to be inverted from this graph. It's just that graph basically flipped. So this time we're going to start off from a high pH, and then it's going to decrease dramatically, and then it's going to taper off. The pH at the equivalence point is still 7 for strong base, strong acid titration. The only difference is here, the pH is increasing, and then for strong base, strong acid titration, the pH is decreasing. But besides that, the graphs, they look relatively similar, just flipped. So whenever you're dealing with a pH curve or a titration curve, you have pH on the y-axis, volume on the x-axis. Now for the titration curve on the left, this corresponds to the volume of the strong base that was added to the solution. Here, this corresponds to the volume of the strong acid that was added to the solution. And the equivalence point occurs when the curve is essentially vertical. So whenever you have like a slope that's very steep, almost vertical, that's where the equivalence point is going to be located. Now, what about a weak acid, strong base titration? How can we draw a pH curve for that? So because we're starting with an acid, we're going to start with a low pH. But it's going to be a little bit higher than the strong acid, strong base titration, assuming the concentration of the weak acid and the strong acid are the same. So let's start with a value that's slightly above 2. So the pH is going to increase, and then it's going to become somewhat vertical, and then it's going to taper off again. So it's somewhat similar to the strong acid, strong base titration, but it varies. And the variation has to do with the Ka of the acid. Now, for a weak acid, strong base titration, the equivalence point is above 7. It could be 8, it could be 9, it could be 10. It really depends on the Ka of the acid and the concentration as well. But for the most part, at the equivalence point, the pH is greater than 7. And if you think about this conceptually, let's say if the weak acid is ammonia. If we react ammonia with a strong base like hydroxide, we're going to get water, and we're going to get the weak base NH3. So imagine if we have 1 mole of ammonia, 1 mole of hydroxide. These two will react to completion. They will decrease by 1, becoming 0. This will increase by 1. So at the equivalence point, we're not going to have any more weak acid or strong base. What's going to be left over is a weak base. And the pH of a weak base solution is greater than 7. So that is why at the equivalence point, the pH has to be greater than 7. Because at that point, all you'll have is the conjugate of the weak acid, which is the weak base. And the pH of any weak base solution will always be above 7. So that's the situation that we have. Now, another important thing that you need to keep in mind is that at 1/2 of the volume of the equivalence point, the pH is going to be equal to the pKa. So whatever the pH value here is, let's assume it's 4. The pKa for this acid will be equal to 4. So remember, the pH is equal to the pKa at 1/2 of the equivalence point. And here's the reason for this. So if we go back to this BCA table, before change after, let's say we have 1 mole of ammonia in a 1 liter solution. So the concentration is 1. And we add 0.5 moles of hydroxide. So this would be half of the equivalence point because we have half of the moles of ammonia in terms of hydroxide. And let's say this is 0. So this is going to go to completion. Hydroxide will be the limiting reactant. Therefore, we'll subtract both sides by 0.5. This is going to increase by 0.5. Hydroxide will go to 0. So at half the equivalence point, notice that we have equal amounts of weak acid and weak base. And according to the Henderson-Hasselbalch equation, pH is equal to pKa plus log base over acid. When the amount of base and acid are the same, either in terms of concentration or in moles, you get log of 1. Log of 1 is 0. So this disappears and the pH becomes equal to the pKa. So that's why at half the equivalence point, the pH will be equal to the pKa, and you can identify the Ka of the acid. So once you get the pKa from a titration curve, the Ka of the acid is going to be 10 raised to the negative pKa. So that's what you need to know when dealing with a weak acid, strong base titration curve. Now let's consider a weak base, strong acid titration curve. So because we're starting with a weak base, we're going to start at a relatively higher pH. But not as high as if it would be a strong base. So the graph will be somewhat horizontal, and then eventually it's going to decline, and then it's going to be horizontal again. Now, the takeaway from this is that at the equivalence point, the pH will be less than 7 for a weak base, strong acid titration. So imagine if we have ammonia. Ammonia is a weak base, and we react it with HCl. We're going to get NH4 plus, the weak acid, and Cl minus. At the equivalence point, these two will go to 0, and we're only going to have the weak acid left over. And the pH will be less than 7 at that point. So here, this will be the volume at the equivalence point. And then at 1/2 of that volume, like before, we could determine the pKa of the acid. So let's say this value is 10. So the pKa for this acid, this hypothetical acid, not necessarily ammonia or NH4 plus, this is just some generic acid, generic base. But the pKa of that conjugate acid is going to be 10. But because we're dealing with a weak base, we want to find the pKb of the weak base. The pKb is 14 minus the pKa when water is a solvent at 25 degrees Celsius. So if the pKa is 10, the pKb has to be 4. And once you know the pKb, you can calculate the Kb of the weak base using this. Now let's replace this equation with a more generic version. So here we have the weak base. We'll call the weak base A minus. And we're adding acid to it, which we'll call H plus. And we're going to get the conjugate acid HA. So 10 would represent the pKa, not of the weak base, but of the conjugate acid. 4 is the pKb of the weak base, which is A minus. So when you get the pKa, it doesn't correspond to the weak base. It corresponds to the conjugate weak acid. So make sure you're aware of that. Now, at the equivalence point, you need to know that at this point, you pretty much have mostly HA. The predominant form of the predominant species at this point is HA. At half of the equivalence point, the concentration of A minus will be equal to the concentration of HA. Because at that point, when you have equal amounts of base and acid, the pH is going to be equal to the pKa. At this point, between 0 and half the equivalence point, you have more of the base than the conjugate acid. Between half the equivalence point and the equivalence point, you have more of the acid and less of the base. And at the equivalence point, the amount of weak base and strong acid that you have is almost 0. I say almost because once all of these go to 0 and you get HA, a small amount of HA will go back into this form. It's going to be very close to 0, but a small amount will be dissociated into H plus and A minus. So they don't go exactly to 0, but close to it. But at the equivalence point, nearly, not exactly, but almost 100% will be HA. And then beyond the equivalence point, you're going to have excess strong acid. So this can be excess HCl or excess H2SO4, depending on the strong acid that you're using. Now the next thing I want to talk about is the buffer region. So this region here would be considered the buffer region. That's where we have a buffer solution. Anytime you have a weak acid and the conjugate base in a solution, you have a buffer solution. A buffer solution is designed to resist changes in the pH of the solution. The buffer solution is ideal at this point when you have equal amounts of base and acid. So at that point, that is at half the equivalence point where the pH is equal to pKa, the graph should be somewhat horizontal. It's not going to be perfectly horizontal because as you add acid, the pH will decrease. But depending on the buffering capacity and how good of a buffer you have, this should be somewhat horizontal because the buffer solution will resist changes in the pH. It's going to try to maintain the pH to a relatively constant level. Now, at the equivalence point, the slope should be steep. The equivalence point is going to be the point in the curve where the line is most vertical. But at half the equivalence point, it should be somewhat horizontal. So those are some other things you want to be aware of. when dealing with titration curves. So remember, at half the equivalence point, you have an ideal buffer solution, and the pH should be relatively constant at that point. But at the equivalence point, the pH changes drastically, so the curve should be somewhat vertical at that point. Now let's work on some acid-base titration problems that ask us to calculate the pH at various points along the titration curve. And let's start specifically with a strong acid, strong base titration first. 50 milliliters of a 1 molar HCl solution is titrated with a 0.50 molar sodium hydroxide solution. Calculate the volume of the sodium hydroxide solution needed to reach the equivalence point. So we're combining HCl and NaOH. To calculate the volume at the equivalence point, we could use the dilution formula. M1V1 is equal to M2V2. So M1, that's going to be the concentration of the acid. We have a 1 molar solution. V1 is the volume of the acid, so that's 50 milliliters. M2 is the concentration of sodium hydroxide. V2 is what we're looking for. So let's go ahead and divide both sides by 0.5 m. One divided by 0.5 is 2. 2 times 50 is 100. So the volume at the equivalence point is 100 milliliters. So that's the volume of sodium hydroxide that we need to add to reach the equivalence point. Now let's move on to part B. What is the pH of the hydrochloric acid solution before any OH is added? The concentration of HCl is going to be the same as the concentration of H3O+, because this acid dissociates completely. So when hydrochloric acid reacts with water, it's going to create H3O+ and Cl-. So a 1 molar HCl solution will produce a 1 molar H3O+ solution. So the pH is going to be negative log of the H3O+ concentration. So that's going to be negative log of 1. Negative log of 1 is 0. So the pH of that solution will be 0. Now let's move on to part C. What is the pH of the solution after 30 milliliters of sodium hydroxide has been added? So we need to write a reaction. So hydrochloric acid is going to react with sodium hydroxide. And when hydrogen and hydroxide get together, it's going to form water. And when sodium and chlorine get together, they will make sodium chloride. Now we need to do an ICF table or a BCA table. ICF, initial change final, BCA, before change after. So you could use either one. The results will be the same. What we need to do is we need to get the moles of the initial reactants. So let's start with HCl. We have a volume of 50 milliliters. We're going to convert that to liters by dividing it by 1,000. And then we're going to get moles using the molarity. So a 1 molar solution means that we have 1 mole of HCl in 1 liter of solution. 50 divided by 1,000 is 0.05 liters times 1. So we have 0.05 moles of HCl. Let's do the same thing with sodium hydroxide. So the volume is 30 milliliters. Let's convert that to liters. And then we're going to multiply that by the concentration of sodium hydroxide. So we got 0.50 moles of NaOH per 1 liter of solution. So 30 divided by 1,000 is 0.03 times 0.5. So that's going to give us 0.015 moles. Now the limiting reactant is sodium hydroxide. So that's going to go to 0. Therefore the change will be negative 0.105. It's always going to be the smaller of those two. So this is going to be 0. And if we subtract 0.05 minus 0.015, we're going to get 0.035. And we really don't need to worry about anything on the right, because that's not going to affect the pH of the solution. What's important is that we have strong acid left over after mixing HCl and NaOH. So now let's calculate the concentration of HCl that we have. So it's 0.035 moles. And then we need to divide this by the total volume. So we had 50 milliliters of the acid solution, 30 milliliters of the base solution, so that's 80 milliliters. If we convert 80 milliliters to liters by dividing it by 1,000, that's going to be 0.08 liters. And keep in mind, the concentration of HCl is the same as the concentration of H3O+. And that's going to be 0.4735 m. So that's going to be equivalent to the concentration of the hydronium ion in solution. Now let's calculate the pH. It's going to be negative log of the H3O+ concentration. So negative log of that number will give us a pH of 0.359. So that's the answer for part C. Now for part D, what is the pH at the equivalence point? So what is it going to be if we were to add 100 milliliters of sodium hydroxide to the acid? At the equivalence point, the pH is going to be 7. Remember, this is a strong acid, strong base titration. At the equivalence point, the pH will always be 7 for that type of titration. And you could follow the same steps here. What's going to happen is these two numbers will go to 0. And so you just have pure water. And the pH is going to be 7. Now what about part E? What is the pH of the solution after 125 milliliters of sodium hydroxide has been added? Feel free to pause the video if you want to try that. So the initial number of moles of HCl will be the same. It's going to be 0.05. That's not going to change. What's changing is the moles of sodium hydroxide that were introduced into the solution. So we have to recalculate that. Let's start with the volume of NaOH. So it's 125 milliliters. Let's convert it to liters by dividing it by 1,000. And then let's multiply it by the concentration of the solution. So 125 divided by 1,000 gives us a volume of 0.125 liters. Multiply that by 0.5, and we get 0.0625 moles of sodium hydroxide. So notice that the volume is beyond the equivalence point. The equivalence point occurred at a volume of 100 milliliters. So we're going past the equivalence point. We're going to have excess hydroxide in the solution. So the pH is going to be above 7. The limiting reactant this time is hydrochloric acid. So we're going to subtract by the smaller of those two values. HCl is going to go to 0. NaOH is going to be 0.0125 moles after the titration. Now let's get the concentration of sodium hydroxide. So let's divide this by the total volume of the solution. So we mixed 50 milliliters of acid with 125 milliliters of base. Therefore, the total volume of the solution is 175 milliliters. And we need to convert that to liters. If we divide 175 by 1,000, that's going to be 0.175 liters. So that gives us a concentration of 0.07143 m. That's the concentration of hydroxide. So what we're going to do now is we're going to calculate the pOH of the solution. The pOH is negative log of the hydroxide concentration. So we're going to take this number, plug it into that equation. Negative log of 0.07143. That gives us a pOH of 1.146. Once we have the pOH, we can calculate the pH. The pH is 14 minus the pOH. So it's 14 minus 1.146. And we can round this answer to 12.85. So that's the pH of the solution after 125 milliliters of sodium hydroxide has been added. Now let's move on to our next example problem, and that is a titration between a weak acid and a strong base.